t, q as a function of time would be just q0 e to the minus t over rc. What if I want the current as a function of time? The current, I of t. What did we say current is in this case? Negative dq dt, yeah. Minus dq dt. Take the derivative, you get minus 1 over rc, but the minus sign will take care of that, so it becomes plus. So it's q0 over rc e to the minus t over rc, right? But what is q0 over c? What's q over c? That's the initial voltage on the capacitor. So this is the initial voltage. So it's the initial voltage over R. Well, V over R is the current. And so, yeah. So in this case, both charge or current will drop as a function of time. So it will decrease as time goes on. Now this constant, notice this RC thing, 1 over RC, appeared over there and over here. So this RC is referred to as the tau, called tau, and it is the time constant. So to charge or discharge a capacitor, if the resistance is small, then tau will be small, right? If R is small, then the tau will be small. So if it's a tiny resistance, then it's quick to discharge the capacitor. Imagine if I didn't have a resistor, if I just hook the positive end of the capacitor to the negative end, it will discharge immediately because R will be 0, and so tau will be 0, so the capacitor will discharge immediately. And if it's large capacitance, it will take longer to discharge than if it's a small capacitor. Yeah. So I want to do one more calculation. So, well, let's stick to this one here, with this one. So, I mentioned earlier about power, right? So before we discharge the capacitor, how much energy do we have? We have Q0 charge.
1/2.
So how much energy do we have? I heard the word 1/2, yeah?
1/2 CV squared.
Yeah, so the initial energy in the capacitor is U0. It is 1/2, you can call it CV squared, or it's Q squared over 2C, right? Q0 squared. That's the energy in a capacitor. Yeah? That's the initial energy. Now, as you discharge the capacitor, when the capacitor is now fully discharged, how much energy is stored in it? 0. So, where did the energy go to? It went into heat in the resistor, right? So the question is the heat dissipated, given away, all that energy given away by the resistor, if we sum it up, will it equal to this?
No, because we lose it.
You lose it in heat, yeah. So if I add all the heat, will I get it back? Okay. Well, let's see. If we don't, we would be violating conservation of energy. So we should.
Okay.
So we will, yes, in fact, we will get it back. So how do we get it back? Well, here is how it works. So the power in the resistor, the energy given off in the resistor per unit of time, what was it? Did I erase it? It's I squared R, right? I squared R. So the power is I squared R. But what's I? I is this, right? I need to square this. So it's Q0 over RC and then you square it. So Q0 over RC. I need to make this a little bit farther. So e to the minus T over RC squared times R, right? That's I squared. So, power, maybe. When you square it, you get Q squared, R squared, C squared, and then there is an R. You get Q squared, Q0 squared over R squared on the bottom, but there is an R here, so it just becomes an R. And then C squared. And then I have e to the, what happens when you square e to the minus t over RC? Becomes e to what power?
Negative 2t.
Yeah, negative 2, yeah, becomes negative 2 t over RC, right? Yeah, that's the power. And it is the energy per unit of time, dE dt. dE dt. So this is equal to dE dt. So the question is, let's solve for dE and see what we get. Sum up all that energy given off and see if we get it back. So I got dE will equal to Q0 squared over R C squared e to the minus 2t over RC dt, right? That's dE. Question is, we need to integrate from t equal to 0, that's the starting of the discharge. How long does it take for the capacitor to fully discharge? So here's Q0. How long, so I want Q to be 0, right? How long do I have to wait for it to be 0?
Just another dB.
I don't need to know that. When is this exponential 0?
To infinity?
You need an infinite amount of time. Yes. Yeah. So as t goes to infinity, Q goes to 0. So you have to wait an infinite amount of time. So you have to integrate from 0 to infinity. So integrate that, so you get what? Q0 squared over R C squared. So when you integrate, you would have,
1/2.
yeah, you would have negative RC over 2, and then e to the minus 2t over RC. Evaluated between 0 and infinity, right? When you integrate, because when you take the derivative, the chain rule will give you negative 2 RC, negative 2 over RC. So when you take the derivative, these cancel. So when you take the antiderivative, you have to divide by the exponential. Okay. So this and this and this and this cancel. So you just have negative Q squared over 2C, and this evaluated at infinity. At infinity you get 0, right? When you have e to the minus infinity, you get 0. And at 0 you get 1. So this becomes Q0 squared over 2C. As it should be. So that's the energy given off by the resistance. So this chapter is done. And so, yay, Thursday we're going to start magnetism then. That's chapter 29. So, I'm going to pause this.